So just read the question once and try it on your own first. So which of the following is not a valid deadlock prevention scheme? So first of all, whenever you read this deadlock prevention scheme, what are deadlock prevention schemes? These are some methods with the help of which we can prevent the deadlock to happen. So we know that there are four conditions. There are four conditions which are necessary for deadlock to occur. What are those? First is mutual exclusion. The second is no preemption. The third one is hold and wait. The fourth one is circular wait. And we know that these four are necessary conditions for a deadlock. Right? So if any of these four conditions are not met, then we cannot have a deadlock. So what are deadlock prevention schemes? Deadlock prevention schemes are those which prevent these conditions to fulfill. Okay, so let's just go through the option. The first option says that release all the resources before requesting a new resource. So if we are forcing, let's say we have a process P1 and it is holding resource R1 and the resource R2, right? And it wants a resource R3. So if we want to release all the resources before requesting a new resource, we are forcing this process to release all the resources. Hence, we are not allowing the hold and wait condition to satisfy. Hence, this is a valid deadlock prevention scheme, right? This is a valid deadlock prevention scheme. The second option says that number the resources uniquely and never request a lower numbered resource than the last one requested. So if let's say we have a process P1 and we have a process P2, right? And we are saying that we will not allow a process to request a lower numbered resource, right? We are not allowing the process to request a lower number resource. So let's say P1 wants the resource R1 and P2 wants a resource R2. Now P1 wants a resource R2 and P2 wants a resource R1. If P1 gets the resource R1 and P2 gets this resource R2. Now, since we are not allowing a lower numbered resource, request to a lower number resource, we are not allowing that. That means P2 cannot request this. Hence, we are avoiding this circular wait conditions. Hence, this is also a valid deadlock prevention scheme, right? And the third option says that never request a resource after releasing any resource. Okay. So it is saying that never request a resource after releasing any resource. So let's take an example. Let's say P1 and P2. So we want to create a schedule such that it is not requesting a resource after releasing any resource. So let's say P1 request for the resource R1 and P2 request for the resource R2. Now P1 request for the resource R2 and P2 request for the resource R1. We can say that if P1 starts executing and it gets preempted after this R1 resource is allocated to this P1. So P1 has been allocated this R1 resource. Now P2 starts executing and it gets preempted after this R2 resource is allocated to this P2 process. So P2 process has been allocated this R2 resource. Now the P1 process is requesting for the resource R2 and the P2 process is requesting for the resource R1. That means P1 is waiting for some resource to be released by P2 and P2 is waiting for some resource to be released by this process P1. Hence, we can see that there is a situation of deadlock. There is a deadlock. Hence, we cannot say that this is a valid deadlock prevention scheme. So, this is an invalid deadlock prevention scheme. So, the question was asking which of the following is not a valid deadlock prevention scheme. That is why this is the answer. Right? Let's also look at the fourth option. Request and all required resources to be allocated before execution. So if we are forcing a process to request all the required resources before the execution starts, that means that we are not allowing to the process to hold and wait. Hence, this is also a valid deadlock prevention scheme. Right? So the answer is option 3. So let me revise again. So we know that there are 4 different necessary conditions for a deadlock. First is mutual exclusion, second is no preemption, third is hold and wait, and fourth is circular wait. The first option was wrong because it did not satisfy the condition hold and wait. Hence, it was a valid deadlock prevention scheme. The second option was wrong because it was not allowing the circular wait condition to fulfill. Hence, it was also a valid deadlock prevention scheme. The third option. So we saw a schedule where there was a deadlock despite satisfying this condition. So that is why this was not a valid deadlock prevention scheme. And the fourth option also was not allowing the hold and wait condition to satisfy. Right? If you have not understood the solution, just go to the solution again and try to revise the conditions for deadlock. These conditions were the thing that you need to remember to solve this particular solution. Right? So see, if you want to revise in an interactive manner, just go through your notes once before seeing the videos of this particular course, the RIC of operating systems, and then just see the question, try to solve the problem, and then see the solution. You will see that what particular topics we have to revise, what particular topics we are lagging behind. That will help you to just track your progress, right? And you will also be able to practice the problems. So let me move on to the second question. Right. So just try it once, just pause the video and try the question once. Right. So we have been given that there are M0 to M4. These are mutexes. So we have an array of mutexes. Let me just create an array. Which is 0, 1, 2, 3, and 4. So we have 5 mutexes and all these are binary semaphores. What are binary semaphores? Binary semaphore take values from 0 or 1. Right? So let's assume that initially all the values of these mutexes were 1. So all the values of these mutexes were 1. That means that the resources that are being logged by this particular mutex is available currently, right? And we also have 5 processes. We have 5 processes from P0 to P4. From P0 to P4. Right? So suppose each process Pi executes the following code. So we have been given the code for every process, which is the code for Pi process is wait for the mutex mi, wait for the mutex mi plus 1 mod 4, and this is the entry section. Then we have the critical section of the process, and after that we are just releasing these mutexes. We are just releasing these mutexes. Mod 4, right? So let us assume that the P0 process starts executing. So the P0 process start executing, and it's execute till this wait mi instruction. So it executes this wait mi instruction and then it preempts. So the P0 process has this resource, has logged this mutex M0. So let me just write 0 here. It means the 0th resource or the 0th mutex is logged by this particular process. And again, if we see the P1 process, and it also gets preempted while executing after executing this particular instruction. So we are assuming that all the processes gets preempted after executing this wait mi instruction. So when P1 process will execute, then the M1 mutex will be logged by this particular process. And similarly, we can say that the mutex M2 will be logged by P2, mutex M3 will be logged by P3, and mutex M4 will be logged by P4. Right? Now, the second statement, the statement after this wait mi command, so we have this wait mi plus 1 mod 4. So as we can see that for process P0, for process P0, it was first waiting for M0 and it was then waiting for M1, right? So for P0, it was waiting for M0, M0 or and then it is waiting for M1. We know that the M1 mutex is already logged by the process P1. So we can say that the process P0 is waiting for some resource to be released by the process P1, right? And similarly, the P1 process. So the P1 process was waiting for the mutex M1 and then it is waiting for the mutex M2. However, this M2 resource is has been logged by the process P2. So P1 process is waiting for some resource to be released by the process P2, and similarly P2 is waiting for P3 and P3 is waiting for P4 and P4 is waiting for P0. How? P4 was waiting for mutex 4 and P4 is now waiting, so it is waiting for the mutex 0. Right? So we have a circular wait here and this leads to a deadlock. Right? And if we try to remember, so we have to solve this entire problem like this and it took a lot of time, right? However, if we had revised our subject, then we can easily see from this particular code that it is the code for the problem of dining philosopher's problem. Right? What is dining philosopher's problem? So in dining philosopher problem, there are, let's say, 5 philosophers. So there are 5 philosophers sitting on a table, and there are forks that are kept on the table. Now, every philosopher needs 2 forks to eat his meal, right? However, this particular philosopher picks this particular fork. This particular philosopher picks this fork. This fork is picked by this particular philosopher. This fork is picked by this philosopher. This fork is picked by this philosopher. Right? Now, this philosopher the philosopher, let's name these philosophers A, B, C, D, and E, right? Now the philosopher E is waiting for this particular 4. However, it is not able to get this because the philosopher D has held it, right? So we can see that here is a situation of deadlock, right? So the answer is deadlock. So the first option says that thrashing, but this is not thrashing. The code is nothing related to thrashing. Why? So if we try to see thrashing, what is thrashing? Thrashing is a concept where even so thrashing is a concept where if we increase, so here at the x-axis we have the degree of multi-programming, and at the y-axis we have CPU utilization. CPU utilization. So if we increase the degree of multi-programming, initially the CPU utilization starts increasing. However, because of the page fault, the CPU utilization starts decreasing, and it keeps on decreasing with increasing degree of multi-program. And this concept is known as thrashing. Right. So we will be revising these concepts alongside solving this question. I will not be only solving this particular question. I will also try to revise the concepts. Right. So the answer for this particular question is deadlock. Let's move on to the next question. Yeah, this is a very good question. So this question is based on some application, and if you know the terms resolution, if you know that how many bits are required to represent how many colors, then you will be able to solve this question easily, right? So just first try to solve this problem. So and then look at the solution, right? So let me just solve it. A graphics card has onboard memory of 1 MB, right? Let me just write this information. So we have been said that we have a memory of 1 MB, which is 10 power 6 bytes, or which is also equal to 2 power 20 bytes, right? So which of the following modes can the card not support? Which of the following modes can the card not support? So let me just introduce with that. Let me just tell you what is resolution, right? So let's say if we have a computer screen, we have a computer screen, right? And this particular screen we can say is divided into a grid. We can say it is a grid, and every particular unit in this particular grid, right? So every unit is known as the pixel, right? And what is resolution? So resolution is the number of pixels at this particular side and the number of pixels at this particular side. So this is known as resolution. So if we have X number of pixels vertically and Y number of pixels horizontally, that means the resolution of the screen is X cross Y. The resolution of the screen is X cross Y. So we have been given the options in the format that we have been given the resolution of the screen, and we have also been given that how many colors this screen support. So let's say if we want to support, let's say if we want to support 8 colors, right? If we want to support 8 colors. So we know that how many minimum bits we require to represent 8 different values, right? How many different bits we require? So the answer is log base 2 8. That is 3 bits, right? So if we want to calculate how many bits are required to represent these 16 million colors. So it will be log base 2 16 million. Right? So we have been asked which of the following modes can the card not support, right? So what we will do is we will start with the largest option. By largest option I mean is with the highest resolution and with the maximum number of colors that the screen support. So we can see that here the resolution is higher among the option A and the option B. However, the number of colors supported is higher in the option B. So let's just look at how much memory is needed to represent such a screen, right? So but let's say the given resolution is 1600 cross 400. That means we have 2 power 4 into 2 power 2 into 10 raised to the power of 4 pixels, right? And every pixel represents how many colors? It represents 16 million colors. So it represents 16 million colors. As we have seen that how many bits are required to represent these 16 million colors, it will be log base 2 16 million. And we can say that it is log base 2 2 to the power of 4 into 2 to the power of 20. Right? So it will be 24 bits, which is 3 bytes. Right? Now we have these many pixels. So what is the total memory required? It will be number of pixels into size of each pixel. Right? Right? And what will be the size of each pixel? It will be equal to 3 bytes. And the number of pixels are 2 power 6 into 10 raised to the power of 4. If we solve it further, that will be 64 into 3 into 10 power 4 bytes. This will be equal to 192 into 10 power 4 bytes equals to 1.92 into 10 power 6 bytes, which is nearly equal to 1.92 MB, which is greater than the available 1 MB of memory, right? So we know that this particular monitor will not be supported by the chip on the graphics card on the board, right? If you try to solve all other options, you will see that the total memory required will be less than or equal to 1 MB, right? So the answer to the solution is option B. Okay. So just try to, I know these questions are tough. Just try to solve these problems once, and if you are stuck, just try to look at the solution again and again. Because these are very important questions and such questions can be seen in the exams, right? Just give 1 month, just try your best for 1 month, right? Try your best for 1 month just. Right? Just give your best. So let's go to the next question. So look at the question first. So it has been given that consider a virtual memory system with FIFO page replacement policy. FIFO page replacement policy is first in, first out. Right? And for an arbitrary page access pattern, increases the number of page frame will in the main memory will increasing the number of page frames in memory will. So instantly from FIFO, you should remember that FIFO suffers from Pallady's anomaly, right? And what is Pallady's anomaly? That even if we increase the number of page frames, even if we increase the number of page frames, sometimes, sometimes the number of page faults also increases, right? And this anomaly, we can see that this particular observation is counterintuitive. However, FIFO suffers from this Belletti's anomaly, right? So let's see the option. So it says that increasing the number of page frames will always decrease the number of page faults. No, because we can see that increasing the number of page frames can sometimes increase the number of page faults as well, right? Second option says that always increases the number of page faults. No, again, because it not always increases, sometimes increases the number of page faults. Sometimes increase the number of page faults. Yes, and this is what is Belodi's anomaly is. Never affect the number of page fault. Completely wrong, because increasing the number of page frame will definitely affect that how many page faults are there, right? So let me just revise few things that how which scheduling which scheduling algorithms suffers from Melody's anomaly, right? And the answer is first is FIFO. The second one is second chance. And the third one is random page replacement algorithms, right? And the LRU and the optimal page replacement policies, these do not do not suffer from page replacement policies. Sorry, do not suffer from Benedict's anomaly, right? Just remember these three scheduling algorithms which suffers from Benedict's anomaly, right? So if let's change the question. So if it was given the LRU page replacement policy, we have to answer this question for the LRU scheduling algorithm. Then what will be the answer? So the answer will that it will always decrease the number of page fault, right? So for LRU and the optimal policy, the answer will be option A. And for FIFO, second chance, and the random page replacement algorithms, the answer will be option C, right? So just remember this, that what is Belletti's anomaly and which algorithm suffers from scheduling suffers from this anomaly, right? So these types of questions, the four questions we have just solved, all these questions can be asked in exam for 1 mark, right? So for 1 mark, they usually ask these questions from the small concepts. You have to revise these concepts, otherwise you will uh, lose these marks, right? It is very easy. It is very easy to score marks in operating systems. So let's just move on to the next question. Just read the question first before moving on to the solution, and try to solve it on your own, right? So suppose the time to solve a page fault is on an average 10 milliseconds, right? So we have been given that the page fault time, the time to solve the page fault is equal to 10 milliseconds, right? And while a memory access takes 1 microsecond, so the time to access the memory is 1 microsecond, second. So during my GATE preparation also, I had this particular doubt, and I know that many students will be having this doubt, that what is included in paid for service time. So in paid for service time, the time to check if the page was present in the main memory or not, plus the time to load the page from secondary memory, right? Plus the time to read from from main memory. All these three components are already present in page fault service time. So we do not need to add the time to check the memory and then time to access the main memory. So by default, all these components are there in page fault service time. If it is explicitly mentioned that this particular thing is not added in the page fault service time, then you need to take care of that, right? So we have been given that the hit ratio is 99.99%. So the hit ratio is 99.99%. So for these type of question, don't need to remember any formula, right? So let's say if the hit ratio is 99.99%, right? And we were having 100 memory access. We were having 100 memory accesses. So if we have a hit ratio of 99.99 times, it means that out of these 100 times, 99.99 times, how many seconds it took to get the page? So it is equal to the memory access time, which is equals to 1 microsecond. And for the remaining 0.01 time, it took around 1 millisecond, right? So it took around 10 milliseconds. Just rewrite that again. 10 millisecond, right? If we convert this to microsecond, then how many second it will be? 10 into 10 cube microsecond, which is equals to 10 power 4 microsecond. Now we have been asked that what is the average memory access time? So whenever we see the term average, we know that average is equals to total time divided by the number of memory access. Number of memory access. So how can we calculate the average? The average will be equals to 9.99 into 1 microsecond. So it took around this much time when we had a hit, and plus 0.01 times it took 10 power 4 microseconds. And what was the total number of memory access? It was 100, right? And if we solve it further, it will be 99, it will be 0.9999, because I am just dividing this by 100, 99.99 microsecond plus 0.01 into 10 square. I am dividing 10 power 4 by 100 microsecond, which is equals to 0.9999 plus 1 microsecond, which is 1.9999 microsecond. And this is our final answer. So if we see the options, the option A is saying 1.9999 milliseconds, right? So just be careful. GATE always plays with the option. We have to remember that the units is microsecond. It was 1.9999 microsecond, right? So option A is wrong because it has been given millisecond here. One is not correct. This is not correct, which is 1.99 microsecond. So the answer is option D. right? So we have to be very careful. We have to just read each and every word of the question, because every word can just change the answer of the solution, right? Change the answer of the question. So just read the questions very carefully, right? Give at least 30 seconds to read the question. That can help you a lot to reduce your silly mistakes. If let's say if this question was of 1 marks, right, and you solved it completely, you took around 2 minutes to solve this problem. However, you did not read this milli. Now it will be minus 0.33, right? Just because you were in a hurry, you lost around 1.33 marks, which can just shift your ranks by hundreds, right? So you have to be very careful while reading your questions. Okay, so just let's move on to the next question, right? So just read the question. If you know the concept of swap space, just try to solve this problem. Otherwise, no problem. I will be telling you what swap space is. Okay, so let me just introduce you about swap space. So what is swap space? It is a temporary storage in the disk, which is used by the operating system to store the pages of main memory if there is no space left in main memory, right? So swap space is used by the operating system to temporarily store the memory image, or to temporarily store the values that are present in the main memory. If we want a higher priority process, if we want a higher priority process in the main memory, then the memory image of a lower priority process have to be kept somewhere, right? So it will be kept in the hard disk. It will be kept in a persistent storage. We need to keep it in a persistent storage. And since we are keeping it in a persistent storage, when we hibernate, when we hibernate our computers, then also the complete memory image is stored in the disk, which is our persistent storage, right? So let's see the option. Where does the swap space reside? So if we try to keep it in the RAM, then we will not be having this persistent storage, right? So the answer RAM is not correct. Yes, we store the swap space in the disk. We cannot store the swap space in the ROM. Why? Because it is the read-only memory, right? How can we write in a read-only memory? So this is not the answer. And on-chip cache is also not a persistent storage. So this is also not the answer. So just remember what is swap space, and you will be able to solve these questions. So this question can also be asked in the GATE exam for around 1 mark. Okay. So moving on to the next question. Using a larger block size, in a fixed block size file system leads to. So we have been given that we are using fixed block size file system. We have to remember this. So immediately we have to see two keywords. We have been given that we have been given larger block size. Also, we have been given fixed block size file system, right? So let's assume that, and we have been asked that what will be the effect on the throughput and what will be the effect on the disk space utilization, right? So immediately we have to see, let's say, if we have been given the hard disk, right? And let's say these are the blocks of the hard disk, right? If we increase the size, we increase the size of the disk block, then if we have a smaller file, if we have a smaller file than the block, then this particular space will be wasted. It will lead to what? It will lead to internal fragmentation, right? If you have revised, then you will know what is internal fragmentation. Internal fragmentation is that this space which is wasted because a smaller part of a block was used to store a smaller file, right? So hence it will lead to poorer, a poorer disk space utilization, right? So this answer is not correct. This answer is not correct. Just try to reduce the number of options you have because you have to save time in GATE exam, right? We want to solve the question in around 2 minutes to 3 minutes, right? And we want to save some time because see, OS is a subject where we can see these type of theoretical problems. And if we know the concept, if we know the concept very clearly, then we can try to save some time here. We can try to solve these problems in around 30 seconds or in 1 minute, right? Let's say if you already knew that what was swap space, then how much time it will take to solve this problem? Hardly 30 seconds, right? We have to save some time in these type of questions so we can give more time to harder problems. This can help to maximize your score. We have to maximize our score in order to improve our rank, right? So we can see that here the option said better disk space utilization and also here better space utilization. So the answer is not better space utilization. Now it is asking about the disk throughput, right? So if we know that, let's say if we have the disk, right? How the disk works? We have multiple platters, right? And then let's say this is the support and we have this hands, right? We know that if we want to access, let's say this particular block. So we knew that then when this disk will rotate and we have to also move this hand, right? And it takes some time. It takes some time to move this hand from here to here. Let me just draw it more clearly. So let's say this was the platter. This was the center. And let's say our block was present somewhat here, right? Now, this is the hand. So we have to move our head from here to here and it takes some time and it is known as seek time, right? And we know that seek time is the most, we can say it is the time to seek is highest. You can say it is highest, right? So if we have larger blocks, then we don't need to, and if we want to, let's say if we want to transfer a very large file, right? So if we want to transfer a very large file, then if we have increased block size, if we have increased block size, so that particular large file can be stored in smaller number of blocks, right? We can store it in smaller number of blocks. And since these are stored in smaller number of blocks, we need less number of seeks, right? And hence, since the number of seeks are less, it will be faster, right? So we can say that it will give us better disk throughput and poorer disk space utilization. So the answer will be A, right? So we have to remember two things here. We have to remember that if we have been given fixed block size, then there will be some internal fragmentation, right? And that could lead to some wastage of disk space, right? That is why poorer disk space utilization. And now we want, if we have increased block size, then a large file, let's say we have a block size of 4 bytes and the file size was 12 bytes, right? Then, and let's say if we had a block size of 2 bytes. So for block size of 2 bytes, it will take around 6 blocks, right? And for block size of 4 bytes, it will take 3 blocks. So here we have 6 seeks, and here we have 3 seeds. So this can increase the throughput of our disk. That is why it will give better disk throughput. So the answer will be A. Moving on to the next question. Just read these questions first. These type of questions are very common in GATE exam. The questions about user level and kernel level threads. So recently there have been asked many questions on this particular topic. So let's just revise this particular topic first before solving the question. We have user level threads and we have kernel level threads. Right? So we know that the user level threads are transparent to the kernel, which means it is not known to the kernel, right? So the kernel is completely unaware of these user level threads. And here, kernel knows about the threads. So since the kernel is not aware of this user level threads, if we try to block a single thread, it will block all other threads, right? So single thread block can block all other threads. I mean, it will block all other threads. However, for kernel level thread, single thread block will not affect will not affect other threads, right? The third one is that context switching is faster in user level threads. Here, the context switching is slower, right? And yes, that's pretty much it. You have to remember these points, and if there are many other points, we can just see the question and I will add points to this particular topic here. So just try to revise the concept of user level threads and kernel level threads. If you just remember this particular point that the user level threads are transparent to the kernel, then of course we can just devise the next point from this particular point, right? Because if the user level threads are not known to the kernel, then blocking a single thread will block all other threads, of course, and the context which is faster in user level thread because the kernel is not taking part in the context switching, right? That is why it is faster in user level threads. You only need to change the register values. And here the kernel knows about the thread, so a single thread can be blocked. And context switch is slower because here the kernel is intervening in the context switching process, right? So let's just go through the options here. So the first option says that context switch is faster with kernel supported threads. We have seen that context switching is slower in kernel level threads, right? So this is wrong. The second option says that for user level threads, a system call can block the entire process, right? We know that the user level threads are transparent to the kernel. Hence, a system call can block the entire process. Yes, this option is correct. So just write what. So we have been asked what are which of the following is true. Just write at a separate place that which of the following has been true. So there can be silly mistakes here. We know the entire concept. However, we can still make mistakes if we are not very careful, right? So just write the options which are correct. So second is correct. The third option says that kernel supported threads can be scheduled independently, right? Kernel supported threads can be scheduled independently. So this is correct because we know that kernel is aware of these threads. So these threads can be scheduled independently, right? So the option C is also true, right? The fourth option says that user level threads are transparent to the kernel. Yes, we know that the kernel is not aware of the user level thread. So the answer will be 2, 3 and 4. So it will be option A, right? So we just have to remember these concepts. If we know these concepts, then we can solve these type of question in just 1 minute, right? And these question can come for 1 to 2 marks in GATE exam. So this type of question can also be asked in MSQ, right? Instead of MCQ, this could have also been asked in MSQ, and MSQ can easily give you 2 marks in just 1 minute, right? So we have to keep these concepts at the tip of our fingers, right? So moving to the next question. So just see the question first before seeing the solution. Just try to solve it on your own. So it has been given that in a system with 32-bit virtual addresses. So it is 32-bit virtual addresses and 1 KB of page size. So let me just write this information. Always write these information, otherwise you have to read these questions again and again, right? It will take a lot of your time. So just write the information. It has been given that the virtual address size is 32 bits, right? And the page size is given to be 1 KB. Also, we have been given that they are using one level of page table. So there is a single level paging and for virtual to physical address translation, right? This is not practical because of. So they are saying that use of one level paging is not practical in this particular scenario because of. So let's see. So we have been given a 32-bit virtual address, right? Out of this 32-bit virtual address, let's say this is our page number and this is our offset, right? So 1 KB is equals to how many bytes? It is 2 power 10 bytes, right? And for 2 power 10 bytes of page, we need how many bits to represent 2 power 10 bytes? We need 10 bits, right? And the remaining bits are the page number. So we have 22-bit page number, right? And let's suppose that the frame number is equals to 1 byte. Okay. Also, let's assume that is equals to 1 byte. So we have how many? We have 22-bit of page number, right? So we know that how many pages will be there in a particular process. It will be equals to 2 power 22 pages, right? And let's say if this is our page table, since we are using only a single level page table, we will have only one page table. And since there are 2 power 22 pages, the number of entries in this particular page table will be equals to 2 power 22, right? And every entry we have the frame number plus some extra bits, right? And I'm assuming here that this is equals to 1 byte. So what will be the size of page table? What will be the size of page table? Will be equal to 2 power 22 into 1 byte, which is equals to 4 MB. We know that the page size is equals to 1 KB and the page table size is 4 MB. So the page table itself will span across multiple pages, right? So that is the problem here. So it has been given that use of one level page tables for virtual to physical address translation is not practical because of. So it has been given the large amount of internal fragmentation, large amount of external fragmentation. See, the internal fragmentation or external fragmentation. First of all, in paging, there is no external fragmentation. So external fragmentation is not possible in paging, right? And the first says that it has large amount of internal fragmentation. The amount of internal fragmentation depends upon page size and not the levels of page table, right? So this is also not an answer. The third option says that the large memory overhead in maintaining the page table, right? Because since we have 4 MB of page table, this is very large. This is very large. So we have a large memory overhead, right? To maintain the page table. Hence, this is correct. The fourth option says that the large computation overhead in the translation process. This is completely wrong because it is in case of multi-level paging, right? The the computation overhead is in case of multi-level paging. This is completely wrong. So the answer is large memory overhead in maintaining the page table, right? So we can see that these types of questions are, if we know the concepts, it is very easy to score marks in operating system. So if we see the subjects in GATE exam like operating systems, COA, data structures, algorithms, and and DLD. So for operating systems and COA, many students are afraid of these subjects. However, these subjects are very easy to score if we know the concept, if we know the basics thoroughly, right? If we know the basics thoroughly, right? So just try to revise the concepts at a regular intervals and try to solve each and every problem from this particular course. You can score almost full marks from these two particular subjects. So it has been seen that around 8 to 10 marks is regularly asked in operating systems. So just don't miss these 8 to 10 marks, right? Because it is very easy to score these operating systems, and it is very easier to score an operating system as compared to some difficult subjects like computer networks and some difficult problems in discrete mathematics, some problems in algorithms, right? And also, if you see the courses from ADSR, you will be able to score marks from this data structure algorithm part, right? Just try to score as maximum as possible from these 4 courses. Also, the courses theory of computation and compiler design. You just have to practice a set of questions. You just have to practice some set of questions, revise regularly, and be clear with your basics, right? Be clear with your basics. No one can stop you from scoring marks in theory of computation and compiler design if you do these 3 things, right? There are questions on disability. There are questions on disability. There are questions on finite automata. And it is very easy to score on disability questions because we have to just remember some properties of languages, and you will be able to score the marks in disability. And usually there is a question of 1 to 2 marks in every GATE exam in every year, right? 1 to 2 questions from this topic every year. So just try to work as hard as possible in the coming month, and you will be able to maximize your rank, right? You will be able to maximize your score. So let's move on to the next question. Yeah, this question is very good. It was asked in 2022 during my year, and it was one of the amazing questions that was asked during that year. So let's just try to concentrate as much as possible. So let's see. We have been given four processes P, Q, R, and S scheduled on a CPU as per round robin algorithm. So the given algorithm is round robin algorithm. The time quantum is given 4 units. Let's write down. The given time quantum is 4 minutes. Right? The processes arrive in the order P, Q, R, and S. So let's create the ready queue. Okay. This is our ready queue. And we have been given that the processes arrive in the order P, Q, R, S at the same time. So the ready queue will be P, Q, R, and S. Right? There is exactly one context switch from S to Q. Let's also write the time quantum here. And there is exactly one context switch from S to Q. So S to Q, there is exactly one context switch, right? Exactly one context switch from R to Q. R to Q also there is exactly one context switch. And exactly two context switches from Q to R. Q to R, there are two context switches. And there are no context switches from S to P. S to P, there are no context switches, right? Switching to a ready process after the termination of another process is also considered a context switch. So after the termination also, if we are getting another process to run, it is also known as a context switch. Which of the following is not possible? Which of the following is not possible as the CPU burst time? See, so there are two particular solutions to this problem. One way is that you can try to solve the you can try to create the Gantt chart for all these four options, right? And you can see which of the following option matches with these particular property, and then you can just solve the question. However, that will take around 4 to 5 minutes to solve this particular problem, right? During my time, I solved this particular problem by solving all the options. However, when I saw the solution, it will hardly take 1 to 2 minutes to solve this particular problem by the method I am going to tell you, right? So just write the number of context switches here, and we have been given this ready queue. So let's write if we have this Gantt chart. So here we are creating the Gantt chart, and so the first process arrives. So the process T arrives, right? So when we are running T, it will run for some time, right? Now we know that there has been given that there are no context switches from S to P, right? So there are no context switches from S to P. If the time quantum or if the burst time of P was greater than 4, if the burst time of P was greater than 4, then the process P would have again gone to the ready queue. However, if the process would have again gone to the ready queue, then there would have been a context switch from S to P. But it has been given that the context switch from S to P is equal to 0, right? So we know that this is not possible, right? So the burst time of P should be less than or equal to 4. So let's see the option. We have been given that option A, P is equals to 4. This satisfies. P equals to 2. This also satisfies. P equal to 4. This also satisfies. And P equal to 3 is also satisfied. Right? So P is less than equal to 4 is a correct. We have to remember this condition, right? Now, the process Q arrives in the ready queue. So till 0 to, let's say, it executes till time some x. After that, the process Q arrives. So Q will be scheduled here. We have been given that there is a context switch from S to Q, right? So this Q process will have this queue process will again to go to the scheduling process, because it has been given that there is exactly one context switch from S to Q. So this process Q should go to the ready queue again, right, to have this context switch, right? So it means that the burst time of Q is greater than 4 for sure. So let's try to eliminate the option. In all the option, we can see that the burst time of Q is greater than 4. Again, we cannot eliminate any option. So let's just go further. We know that we have the process R now, right? Let's say it's execute till Y. Now we have the process R. We know that there is a context switch from Q to R. So there is a context switch from Q to R. This means that Q to R, right? This means that the yeah. So this means that the process R will also be pushed into the ready queue to have this context switch, right? And this context switch off from S to K is already handled. So we will just make it 0. And again, Q to R is also handled. So we'll make it to 1. Now, the process R is again pushed into the ready queue, it means that the burst time of process R is greater than 4. So let's just try to eliminate the option. Again, all the options have burst time greater than 4, right? So we cannot eliminate the option. So the next process to be scheduled is the process S. However, we know that there are no context switches from R to S. Hence, we can say that this process S will not be added to this ready queue again. So the process executes first and then it will not be added to the ready queue again. This means that the burst time of the process S should be less than or equal to 4, right? So let's try to eliminate the options again. We can see that all the options have the burst time of S less than or equal to 4. We are done with the process P and we are done with the process S, right? However, the burst time of Q and R can be greater than 4. It can be greater than 8 also. Let's just solve it further down. So the next process to be executed is the process Q, right? So we know that there is one context switch left from R to Q. Hence, this process Q will again be pushed to the ready queue, right? So we know that this process will be executed again and it will be pushed to the ready queue again. Why? Because of this context switch. So let's make it to 0 and let's make this A, right? Now we can say that the burst time of the process Q will be greater than 8, right? Why? Because it has been executed 2 times. We know that the time quantum of round robin algorithm is 4 and it is still in the ready queue, right? So it means that the burst time of process Q is greater than 8. Let's see the option. We can see that in option D, the burst time is given as equal to of Q is equal to given as 7, right? This means that this is not possible. That means that this is our answer. So it took me some time to explain you guys. However, if you solve the problem, a similar problem in the exam exact same fashion, so you will be able to solve this problem in around 2 minutes. Hence, you can save some time for some much more difficult problems. This was a very good problem according to me, and such similar problems can be seen in exam in the future years, right? So just see the solution of this again if you have not understood it completely. Just try to understand the solution in a very clear manner, right? Otherwise, you can make mistakes in the exam, right? So what I have done is I have written the number of context which is at a side and I have also written the time quantum. Just see that which process will be pushed to the ready queue again on the basis of the number of context switches. And then you can make interpretations about the burst time of the processes, right? So you know that operating systems is a very important subject Not only because of GATE. In GATE exam, we have around 8 to 10 marks of questions every year, right? And these questions are easy to score. So of course, there will be some hard questions that can be from operating systems. However, most of the time, these marks are easy to score, right? You can push your rank using operating system. Second is that this subject is majorly asked in your placements. And remember that operating system was one of the most asked subject in the placements at even IIT, right? So here at IIT placements, operating systems was majorly asked. So just try to be clear with your basics as much as possible. It will not only help you in GATE exam, but it will also help in your placements either at IIT or even if you are preparing for placements at your bachelor's college, right? And also it will help you in your job, right? So operating system is very important, right? So just try to solve these questions as much, just give as much as time you can and try to solve each and every problem of this particular course, right? And try to revise your concepts at a periodic time. I know I am repeating this again and again, but just revise your concepts because technical concepts are very easy to forget. Just try to revise them again and again. Moving on to the next question, right? So just try to remember the state diagram. Just read the question. Just try to solve the problem. Pause the problem and try to remember the state diagram of the process. You will be able to solve this question, right? So moving on to the problem. Consider the problem following statements about process states transitions for a system using preemptive scheduling, right? We have been given that the system is using preemptive scheduling. So let me just first draw the state diagram. So we know that first the process is in the ready state. So when the process is loaded in the main memory, it is known to be in the ready state. Before that is a new state. I'm not drawing that. After that, when the short-term scheduler selects a particular process, then the dispatcher shed dispatches it to the CPU, right? So it moves into the running state. Now, since it has been given that we are using preemptive scheduling, that means that the process can go from the running state back to the ready state again, right? And after that, once the process completes its execution, it moves to the terminating or the terminating states, right? And if the process is running currently, and it is, if the process is running currently, and it encounters a blocking operation or a IO operation, IO or a wait operation, it moves into a waiting or logged state. Waiting or logged state, right? And once the process completes its IO operation, it goes into goes back into the ready state. It cannot go directly from the waiting state into the running state, right? It is the job of short-term scheduler to select which process will go from ready to run state. However, it does not move any process from the waiting state to the running state, right? We have to remember this. This is very important. We cannot do this, right? So we cannot move from waiting to the running state. Okay, so let's see the option. It has been given that a running process can move to a ready state. Yes, a running process can move to a ready state because we have been given that it is a preemptive scheduler. If here it was given non-preemptive scheduling, then this option would also be have been given, right? So a running process can move to a ready state. This is correct. A ready process can move to a ready state. A ready process can move to a ready state. Yes. I guess there's a typo here. It will be a ready process can move to a running state, right? So we can move from a ready state to a running state. The third option states that a blocked process can move to a running state. This is completely wrong. As I said that it is not possible for a process to move from a blocked state to a running state. A blocked process can move to a ready state. Yes, when the IO operation completes. Right? So this is also correct. So which of the following statements about the transitions were true? So the answer is 1, 2, and 4. Okay. Moving on to the next problem. Yeah. So there have been many questions asked. There have been many questions related to these that have been asked in recent years. So just pause the video and try to solve the problem once. If you know the concept of 4, you will be easily able to solve this problem in 1 minute or even 30 seconds. Right? Just try and see the problem and try to solve the problem. Okay. So we have been given the C program which is executed on a Linux system. Right? And the program is like that. Here a variable I is declared. Then we have a very for loop which is running from I equal to 0 to I less than equal to 10. And so the values of I are from 0 to less than 10. Just write this for clear explanation. Okay. And if I mod 2 equal to 0, this means that when I is even, then there will be a fork call. So we can say that there will be a fork call for I equal to 0, I equal to 2, I equal to 4, I equal to 6, and I equal to 8. So there will be 5 fork calls. You know that if we have n fork calls, then how many child process do we have? We know that it will be 2 raised to the power of n minus 1. And here we have 5 fork calls. So it will be 2 power 5 minus 1, which is equals to 31. And if the question was that how many processes will be there, including the parent process, then it will be equal to 32, right? So just remember this formula. Just remember the formula for the number of child processes, right? And we can solve this problem easily in 30 seconds. Okay. So let's move on to the next question. Right. So consider an arbitrary set of CPU bound processes. So what are CPU bound processes? Which are mostly executed on CPU. It does not have a large IO or waiting operations, right? So these are CPU intensive processes, right? With unequal, with unequal CPU burst lengths submitted at the same time to the computer system. So we have been given that the arrival time are equal for all the processes and the burst time is unequal. So just try writing these small information at a side because that will help you to save some time, right? And that will avoid the silly mistakes that we do in GATE exam. So the question is that which of the following processes or which of the following process scheduling algorithm would minimize the average waiting time in the ready queue, right? So we know that let me use some space from here. So let me just write here. We know that for non-preemptive, non-preemptive algorithm, Yes, shortest time first. And for preemptive algorithms, for preemptive algorithms, SRTF, shortest remaining time first will give the what? Will give the maximum, will give the maximum throughput and minimum average waiting time and the turnaround time. Now see, if we have revised our concept, we can just remember that STF and SRTF are the one algorithms which have minimum average waiting time, minimum turnaround time, and the maximum throughput. We just have to see the option and we can see that option A is SRTF. See, if we remember these concepts, we can solve this problem very easily and in a very short period of time. So we have to save some time in GATE exam by solving these type of problem in a minimum time, as much as minimum time as possible, right? I know I'm repeating this again and again, but this is very important. That is one of the things that helped me to improve my score. So moving on to the next question, question number 15. So the question states that the maximum number of processes that can be in a ready state, that can be in a ready state for a computer with n CPUs. So we have been asked that how many processes can be in the ready state. What is ready state? Ready state is the state when the process is loaded into the main memory. So if we have this secondary memory and when the program is loaded to the main memory, it is known as a process and it is currently in the ready state, right? And the maximum number of processes that can be in the ready state for a computer system with n CPU. So we have been given a system which is a multi-programming system, multi-programming system with n CPUs. We know that this number is independent of n. Why? Because this number is known as a degree of multi programming, degree of multi programming, right? Which means that, so sorry, this will not be multi programming, it will be multi processor system, right? And degree of multi programming, what is degree of multi programming? It is the maximum number of processes that can be in a main memory or that can be in the ready state, and it is it only depends on number one, the main memory size. Number two, the process size. And it does not depend on the number of CPUs in the system. So that is why it is independent of, the answer will be D. So just remember what is degree of multi-programming and it depends on what factors. You have to remember the takeaways from this question is these 2 points, right?